Now, today we are going to discuss briefly the Buchwald-Hartwig coupling. Now, this is one of the fundamental reactions which both Buchwald group as well as Hartwig group have simultaneously reported. Their industrial application has been tremendous. Specifically in the pharmaceutical industry, where many different molecules need to be generated, these are the reactions of choices, or this is the reaction, one of the reaction of choice. What it is done in, this is a simple reaction in a way where you take, let's say, primary amine, you get secondary amine, you get a secondary amine, you get a tertiary amine, or you can take alcohol to give you the ether compound. So you can take a primary amine, you can get a secondary amine. If you are taking a secondary amine, you can get a tertiary amine. Okay. If you are taking an alcohol like phenol or any aliphatic alcohol like methanol, ethanol, you can get an ether out of it. These are very, very exciting transformations. Simple organic reactions will not be that effective because we are talking about a partner which has benzene ring in it. Often this is Rx, we are talking about benzene ring with an halide in there. So these sort of Rx, of course, benzene rings are differently substituted, you can have different substituent in there, right? Overall, these sort of reactions are in any other sense in synthetic chemistry or in organic chemistry is going to be very, very difficult to do. Okay. Now, this R1 over here, it could be aromatic group, that means this benzene ring containing compound, or heteroaromatic, it could have a heteroatom in there, let's say a nitrogen in there, or an oxygen is there, or an sulfur is there. So different aryl and heteroaryl group can be reacting. R2, that means over here, these reactions are these partner can be of different type, primary. So let's say if you are looking at methylamine, you can take CH3NH2, right? Methylamine, simple amine, or you can take even aniline. These are primary amine, right? You can take aniline. Anything with an R group, NH2 group, RNH2, primary amine, right? These are the primary amine. Anything with NH2 group you can take. And from there, what you will get your NH, one of the NH constant, your R was there, R will remain, and another group, let's say R prime, will come in. So this R prime is coming from here. Okay. So this means that a primary amine is going to a secondary amine. Why it is primary amine? Because it was having only one substituent on nitrogen. Two hydrogens are there. This is the primary amine. This is the secondary amine because one hydrogen is left now and two other substituent has come into the picture. So the primary, that is 1 degree amine, give you secondary amine. Now you can look at almost any organic molecule, you will see there is a nitrogen, many, not any, many, most of them, a lot of them will have nitrogen atom in there. Now if the nitrogen atom is there in the molecule, you can reverse this reaction, you can go back and say that perhaps you want to do this Buchwald-Hartwig coupling. For example, over here, see there is a nitrogen, right? And then there is a carbon. This nitrogen and this carbon bond you can perhaps easily prepare, but between this nitrogen and this benzene ring, this bond by many synthetic method or any other organic reaction will be very difficult to prepare. And this essentially is the beauty of this Buchwald-Hartwig coupling, that you can do the reaction between the sp2 center and an amine in particular, right? So going back again, so these sort of exciting reactions where you need to really do this reaction an amine and a benzene ring. So this is something can be done very easily. In over here, for example, you have a nitrogen and carbon bond, right? This bond, that's what we are showing. This bond can very easily be synthesized if you have NHBN. If you look at CH2 NHBN, right, this part, and then in this part you put an halide, aryl iodide, iodine. Now you can do the Buchwald-Hartwig coupling to put this nitrogen and get it connected with this carbon. So you can take this nitrogen and come to here, right, and this H and this I goes as HI, hydroiodic acid, basically will be neutralized by base. Okay, it's a strong base out there now. Does it make sense? Simply what essentially you get an opportunity to do is, if you have R in R prime, let's say, right, and these R prime, let's say this R prime is having a benzene ring, okay, then you can say that you will do Buchwald-Hartwig reaction where R in H2 plus R prime, that means a benzene ring, and X will be there. So if you want to prepare this molecule, which is a secondary amine, there are plenty of secondary amine, plenty of molecule in pharmaceutical like medicine where you need an amine nitrogen, many of them are there. So these nitrogen containing molecule you can synthesize from very simple starting material which are amine. It could, as I said, it could be primary amine or secondary amine. If you start with primary amine, you get secondary amine. And if you start with secondary amine, you get tertiary amine. The great thing is, here you can introduce an aryl group like benzene ring. From here also you can introduce a benzene ring. Just to give an example, let's say you start with aniline, right? This is a simple reaction. You start with aniline and then you get diphenylamine or diarylamine. So this NH, the same benzene ring you get. Drawing has been difficult here in this, and you can get a new benzene ring. Okay, this is the new one. This is the new bond you have formed. Let's say you have an R group in there. From there you can, so what did I say? This is a primary amine. You get a secondary amine, means secondary amine where you have introduced another benzene ring into it. If you start with the secondary amine and again do the Buchwald-Hartwig coupling, you can bring 3 benzene rings together with a nitrogen, another benzene ring, another benzene ring here. Drawing has been difficult. Hand drawing would have been really easy and simple to do. See, so primary you start with, you get secondary, and then you get tertiary as well. Fantastic. Similarly, it need not be, you don't have to start with the aniline, you can start with simple aliphatic amine like CH3NH2 or ethylamine or propylamine, N-butylamine, any amine you want, right? That is where these reactions are so powerful. Not only amine, you can do this reaction also with, you can start with an amine where NH group is there, or you can do this reaction with alcohol. Irrespective of amine and alcohol, you can get a higher amine or a higher alcohol, in this case ether. Okay. Now, as you can see, by utilizing this Buchwald-Hartwig coupling, you can form a new carbon-nitrogen bond. So this bond, which is between the carbon and nitrogen, this bond is prepared by this Buchwald-Hartwig reaction. What reaction demands? Usually a palladium salt, a ligand, a base, and 80 degrees C. Of course, there would be solvent that is also required, right? So just to very briefly mention that this is the one of the very powerful reaction. There are many variants of Buchwald-Hartwig reaction, but this is a simplified version of this reaction where you start with, let's say, bromobenzene or iodobenzene or chlorobenzene or triflet, nonaflet, anyway, benzene ring with an X group in there. Okay, so benzene ring with an X group, this is what you are looking for, benzene ring with an X group, and then benzene ring with an aniline, NH2. Now these two centers will join, as you see this red bond, to give you the amine, right? So that is very powerful reactions. As you can see, this new bond is getting generated. This new bond is getting generated. That would be an exciting transformation, because that will dictate many pharmaceutical synthesis, many material synthesis, right? Usage are limitless. These are fundamental type of reaction. And this becomes more and more useful as we start understanding the strength of it, where you can do this reaction. Almost any organic molecule you can take a look at, and whenever you see on the benzene ring there is a nitrogen outside, you can invariably think of this Buchwald-Hartwig reaction, and it works more often than not. It's an extremely powerful reaction. Okay, now what can we understand from the reaction mechanism? Usually you need a ligand palladium complex. Okay, so the palladium is there and you need ligand, suitable ligand with that. We'll come to that quite a lot. Now this aryl X, usually it's the bromobenzene, let's say, or iodobenzene or chlorobenzene. Let's just take bromobenzene. In this CX bond, palladium will get in. Okay, so in this CX bond, aromatic and X, right? In this bond, palladium will insert. It forms a palladium carbon bond. So you can draw benzene ring in here, and then X, let's say bromine. Okay, let me draw it cleanly one more time. So here, sorry. Okay, so this, if this is this air X, if it is aryl bromide, X would be bromine, aryl group would be benzene ring. So palladium and this benzene ring, this bond is formed. This is what is called oxidative addition, as we have discussed before many a times. Okay, now from there on, this second amine, of course this mechanism is little bit old, it depends on the ligand and other things, but then this second amine can come into the picture, and then the aryl group and this amine, which is nucleophile this nucleophile comes into the picture. Deprotonation means one of the proton from this NH2 goes out, and then aromatic and nucleophile together forms the bond to give you this compound. Okay, is it clear what is happening here then? What is happening here is you are looking at this ARX bond. Inside this palladium is getting in, and this nitrogen through lone pair it binds with palladium, and then this H and X, HX goes out, and then AR, this NH and this benzene ring comes into the picture. Okay, just to tell you one more time what is happening, you have taken aniline, for example, you have taken aniline and bromobenzene, just as an example. Now from there you have inserted palladium here, so X is now exchangeable, you can exchange X. So what happens, then you can take a proton from NH to H, this H and X goes out as HX, like if it is Br, X is, if it is bromine, then it goes out as HBr. Now this HBr can be neutralized by the base, sodium tertiary butoxide, let's say in these cases we are using. Of course other weaker base, more useful base can also be used. Once this HX goes out, this carbon center and this nitrogen center forms a bond that is over here, that's what you see. Okay, that means you are able to generate from one small amine to a larger amine. Primary amine gives you secondary amine gives you a tertiary amine. What is the mechanism? It is roughly shown over here. The mechanism may change a little bit, subtle, depending on the amine or depending on the ligand that you are having on it. Okay, we will discuss to some extent this process. So oxidative addition, amine binding, deprotonation and reductive eliminations are the stages which this catalyst goes through. Let's look at the application. Let's look at how we can apply these knowledges. Now these are some examples. What we are seeing here is a amine and a benzene ring containing either it is a chlorobenzene, bromobenzene, iodobenzene or phenol derived one, but overall a benzene ring with a leaving group X. Of course this sort of reaction is not possible without metal. This has to be organometallic chemistry, this has to be this sort of catalysis, right? Without these reactions in organic reaction, nothing is going to happen to this CX bond. Now once we are trying to do these reactions in this way, we get an opportunity to form a new bond, right? So what you see from this NH, you get this new bond where arene is coming into the picture. I would rather say you draw as NH2 here. Okay, now NH2 give you one H and one X is lost, and then you get that, right? This is simple, right? As you see from the cartoon, intermolecular reaction, two different molecules coming into picture, joining hand to give you a new molecule. Just like what you have seen in the metathesis, two different molecule comes and join. That was a carbon-carbon bond formation. Of course, you lose out some part. Similarly, over here also, two different partner comes out and sits down and give you this molecule. Okay, the applications are limitless. You see the application in medicinal chemistry. There are many countless products in medicinal chemistry, in process chemistry, In material science, different ligand synthesis of natural product, different heterocycles. I think the examples will run out. This itself, this fundamental reaction itself can be taught perhaps over 40 hours or more. Okay. Just like metathesis reaction, this is one of the triumph of really homogeneous catalysis. This gives you strength to make the molecule in a very convincing way. Just to give you some examples. Okay, these are useful compound. Many different pharmaceuticals, drugs are drawn here, although I have not given their names, but these are very, very useful molecule. Okay, we have names in subsequent some of the slides. Okay, so these are the real molecule that is industry is preparing, and they need to use these molecule for sure. Okay, so as you can see over here, this carbon nitrogen bond, as I was saying, between a benzene ring containing molecule and a nitrogen, if there is a bond like this, carbon and nitrogen, whenever there is a bond like this, you can think of Buchwald-Hartwig coupling. Okay, here also there is a benzene ring. Outside benzene ring there is a carbon nitrogen bond, right? So you can think of this as a Buchwald-Hartwig coupling. Here is a benzene ring and there is outside a carbon nitrogen bond. You can do like that. Of course, this bond also you can think towards doing by Buchwald-Hartwig coupling, right? This is also benzene ring. Outside benzene ring there is a nitrogen. You can do Buchwald-Hartwig coupling. Both the cases, two benzene rings, both these benzene ring, of course this is heteroaromatics. You have a nitrogen also inside the ring, right? Pyrimidine, two substituted pyrimidine, but anyway, so both all these cases you are able to do the reactions. You will be able to do the reactions either over here, also over there, if you want, by Buchwald-Hartwig coupling, right? Buchwald-Hartwig coupling, Buchwald-Hartwig coupling, right? Even of course this one, this may be SNAR substrate, but here also potentially you can think of. And as you see all the red ones, so you have to take here a, let's say, bromine, and here it would be NH, that's it. Over here it would be NH2 amine, and over here it would be a bromine, let's say. Okay, depends, of course some of these substrate could be SNAR substrate, different mechanism can follow. Some of these again you can take a bromine over there. Here you can put a bromine, means bromobenzene, and you can take this NH over here, right? You can break this. So these are real molecule, really important molecule. What one thing you would have noticed, you need a palladium catalyst. Okay, and so of course palladium P catalyst is there. Palladium catalyst always you always need a palladium catalyst. Different sources, it could be palladium DBA, dibenzyl acetone, or palladium acetate. We'll come back to these catalysts, palladium catalyst, just simple palladium catalyst later on, but for now let's just focus on this. So all these highlighted, red highlighted bonds, as you see over here, all these are prepared. Not only these, you can prepare actually more, many more carbon nitrogen bonds which are not shown over here by the same method. For example, over here you did not discuss, even over here you can discuss. In addition to, even over here you can do a Buchwald-Hartwig, here also definitely, and so many other places also you can do in addition to this highlighted one. You need a ligand, okay, you need a base, usually strong base. You can also use weak bases. Temperature usually like 80 degrees C. Yield is usually good. You need usually stoichiometric equivalent amount of base. Palladium loading can be decreased depending on the cases. Sometime even the ppm level of palladium can be used. It's not like you have to use always 10 mole percent. You can use 0.0005 mole percentage of the ligand, and this is why specifically excellent ligand, phosphine ligands, usually monodentate phosphine ligands becomes bulky phosphine ligands becomes useful. Of course, some of the bidentate ligand also are useful. These monodentate ligands are popularized by Buchwald's group. Some of these bidentate ligands are popularized by Hartwig group, and many other contributions has been over the decades that have come in. Many other research groups, just like as we were discussing in the context of metathesis reactions, there are like thousands of students, many different research laboratory, hundreds of research laboratory across the world, if not thousands, 10,000 places. These sort of development are going on in industry. Many people are working on developing, applying these methods to make it better. Okay, some of the industry, let's say, having 50,000 people working on in their industry, and quite a good number of these employees are involved in preparing these molecule by utilizing these techniques. So there are lot of people overall involved in developing these reactions. Just like metathesis reactions, these are fundamentally exciting and important reaction, and these are valued in a much wider sense. Here is another reaction, just an example. These are difficult reaction usually, without getting into too much of details. This is an amine. It's an heterocyclic amine, usually difficult reaction to carry out, and these CX, these sort of bromobenzene, let's say, or chlorobenzene, you can form a new bond between carbon nitrogen with a very exciting ligand, as you see over here. Okay, these are Buchwald-Hartwig reactions, one of the favorite ligand developed by Buchwald's group, and it works really wonderfully. Okay, now these reactions, as you can see, the application, these are some of the applications or some of the cases where you can do these reactions. See, these are all are pharmaceuticals, or are in clinical trial, or different level of clinical trial. These are molecule like drug, medicine. The real molecule, real synthesis are done by utilizing Buchwald-Hartwig cross coupling reactions, right? Many, almost, you cannot nowadays, you cannot think pharmaceutical industry not using the Buchwald-Hartwig reactions. They have to, almost they have to, because this is the best out there in the literature. Many molecule preparation in small scale, large scales are done by utilizing these Buchwald-Hartwig reactions. Here is an example, nilotinib, one of the wonderful medicine. You can look it up. It can be prepared as is shown over here. So what you see over here is an amine. It's a cyclic amine over here. This H and this Br goes out, HBr. This new bond is formed, and once, see, this is outside benzene ring, this is a nitrogen. So this is an amine and this is an halobenzene, let's say bromobenzene. Now you form the CBr bond. Now this is done, this bond formation is done by Buchwald-Hartwig coupling, which is fantastic reaction, and it works really beautifully. Not only that, you can strategize in many different ways. This is also another bond that can be generated by Buchwald-Hartwig coupling. Even other reactions, this is an amide synthesis, many other reactions can be done like that. Look it up, nilotinib, and it's huge. You will understand how valuable this molecule has been. Okay, and this sort of preparation sets the standard. Landmark synthesis gives an opportunity to do the better synthesis in the decades to come. Okay, any question at this point? If you
No,
have any
sir.
question, I can take. Okay, okay. If not, we can keep on discussing. So essentially, what we are trying to say here simply is, if you have a benzene ring or aromatic ring, outside that aromatic ring you have nitrogen. There are almost every other compound, every second compound or third compound will have this sort of motif or this sort of requirement. Specifically, you look at any medicine, almost any medicine, 1 out of 3 medicine perhaps will have these sort of carbon nitrogen bond, carbon nitrogen bond. Wherever you see this sort of carbon nitrogen bond, this is going to be the method, most reliable method to prepare this sort of molecule. Industrial applications of these molecules are, or of these reactions are, limitless. Okay, these are, industry are using every day these reactions, and thousands of people are using these reactions, because these are the kind of only way or the most reliable way so far in the literature to prepare these molecules. Okay. Now moving on, there are quite a number of issues. Of course, as in every reaction, as you are saying, there are problems. Okay, and this is where the research and development need to be done over decades, many decades, 30, 40, 50 years, or even more. People need to work on to overcome the limitation, to understand where the problem is and how to solve the problem. Okay, as I was saying, that even let's say some excellent reactions like Suzuki reaction, Heck reaction, Negishi reaction, metathesis reactions, as you have seen, people already got Nobel Prize, but that doesn't mean that these reactions are perfect. These reactions are good. People are trying to make it very good. Okay, I would say, this is debatable whether it is already very good. Maybe it is good, but a lot of effort need to be still put in to make this reaction more useful to the industry, make the catalyst loading low, make the side product formation less, make every reaction really a dream reaction. Usually what happens for most of these, let's say even for any reaction, if you can take up Suzuki reaction, a given set of reaction may be working. If you change the set or the combination, the reaction may not work at all. I mean, that's the problem. Although, I mean, it's nothing to say that it doesn't work, just that you have to have the right combination which works excellently. If your combination A plus B goes to C plus D, right A or right B is missing, then the reaction suffers. And this is particularly why development of a great ligand for metal, great metal system, understanding the mechanism of the reaction becomes much more important than the application even. Okay, when people try to do this reaction, apply this reaction, then people realize the limitations. These are the best reactions out there. Let's say Buchwald-Hartwig coupling, Suzuki coupling, reaction Heck reactions. These are best reactions out there. Metathesis reaction. These are best reactions out there, but still they have many limitations. And this is why, once again, although the reaction type is known, to make it useful to academic lab, to industry for different applications, one need to really work. Decades, sometime perhaps centuries are required. Many people would have contributed to better understand and to make these reactions useful, right? So it's not a one-day development. Discovery may have been the initiation or the beginning of a long journey. Okay, so that goes on, and many processes that goes on. Okay, one of the thing that we also wanted to discuss here is why we kind of use palladium 2 plus, something on the same way we were discussing last 2-3 class before. The real catalyst, if you look at the reaction mechanism, let's go back to the reaction mechanism for a moment. This reaction mechanism, if you look at, this is not palladium 2 plus, okay, this is palladium 0 in zero oxidation state. It's not oxidized species, but when you start the reaction, you essentially, I think it is not really usually that grateful. I'll come to in a moment. Usually we start with palladium 2. Usually we take what? Palladium chloride or palladium acetate. But then we need to generate palladium 0, because palladium 2 is not really doing the reaction in these cases. It's the palladium 0 that is doing the reaction. So this is going to be a palladium 2 species. After oxidative addition, palladium 0 ligand complex becomes palladium 2. Now the simple question is, how do you generate, so this step, how do you generate palladium 0 from palladium 2? Once again, how do you generate palladium 2 to palladium 0? Why don't we take palladium 0 directly? So this is the question. How do you generate from palladium 2 this ligand palladium 0? Because ligand palladium 0 species is the species which is doing the reaction, not this palladium 2. This is not doing the reaction. It's this palladium 0 species, palladium 0 oxidation state with a ligand is doing the chemistry, with a ligand L doing the chemistry, right? How do you do it and why do you do it? Why you cannot take directly ligand palladium 0? Okay, so let's try to understand and address this question today right now. Okay, so the first question is, why don't we use too much of these sort of palladium 0 complex? The most often what we use is palladium 2, palladium acetate. This is palladium chloride or allyl species. These are the ones which are used mostly, and that is because these are cheapest, widely available. Amount of these are quite highly available, of course, readily available. Everywhere you can buy almost, okay, and it works. Now these palladium 0, the problem is, as I said, from palladium 2 you need to generate palladium 0, but not these palladium 0. You generate something else, right? Because you need a different ligand palladium 0. If your goal for this reaction is to generate different palladium 0 ligand species, the ligand is not really DBA or triphenyl phosphine, because these are not really great ligand for the these carbon nitrogen bond formation reactions. You need a separate ligand, outside ligand. The problem is, that's why you don't want to have a competition of that extra ligand that you need to add to palladium with this DBA. The reason you get these palladium DBA 2, 3 or palladium phosphine complex stable is due to the ligand. Now these ligands are not the final ligand, you need another ligand to add. That's why you don't want to start with this ligand, because they will compete with the palladium to bind. Okay, let me rephrase and say it again. You want to generate essentially a ligand palladium 0 species. This ligand is very useful and expensive, very highly designed ligand, because this ligand in that catalytic cycle will be the only ligand which is working really excellent. So this ligand is very precious to you. Okay, very precious to you. Let's say these complex, let's say if it is 30 rupee, this ligand will be 3000 rupees. Of course, you don't want to waste any of these ligands because this is very expensive, not so readily available, and you want to minimize the usage of it. Now, this is where what you do, you start with palladium 2 plus, you reduce it to palladium 0. During this process, you add this expensive ligand to it, so that your ligand palladium 0 species is really generated quite well. That's how we do. On the other hand, from here, if you want to generate, which is already a palladium 0 complex, but palladium 0 complex is stabilized by these ligand, because these are good ligand, it can stabilize palladium 0. Palladium 2 is a stable species, but palladium 0 is an unstable species, right? If you want to buy palladium 0 in these forms, as in here, then you are basically having the stability of this palladium 0. Now the ligand exchange between this DBA and this very expensive ligand of yours will be difficult, because you need to displace or throw it out and put a new ligand. Now that is going to be difficult. On top of that, these ligands are going to be in the solution, so they are always trying to come back on palladium, right? So you don't want to have such competition, because this ligand is the only thing that you need. You don't need an extra ligand, because this will be nuisance. This will create trouble for you. So that's why what it is done, usually palladium 2 plus you start with, you add a ligand and reduce it. During that reduction, ligand palladium 0 species is formed. Is it clear? Okay, I hope so. Let me summarize very briefly. So you start from palladium 2 plus, you reduce it to palladium 0 and add a ligand during that time. You don't start from another ligand palladium 0 species, because that another ligand is not good for palladium 0 for the catalysis. That another ligand, extra ligand, which is coming with your commercial or the purchased palladium 0, because palladium 0 can be stabilized with those ligand, it becomes very expensive, as well as it's competing with your main ligand. You don't want any competition in the main reaction. You want this reaction to be as good as possible, as little palladium loading is required as possible, right? So your catalytic cycle is very much valuable to you. You don't want to give any competition to your catalytic cycle. You want to do it in little, like almost homeopathic amount of palladium. That's the target, right? Tiny amount of palladium you want to use, so that your ligand has to be very effective. And you don't want with your effective ligand something else is competing for your metal, that is palladium. You want to keep the reaction very simple and effective. So that is why it is always preferred that you use very simple, readily available, cheap palladium source, such as palladium acetate, and then or palladium chloride, and then you reduce it in situ in the reaction condition. Together you reduce it, you add a ligand, and then you go ahead. Okay, so this pathway, although this is palladium 0, this is palladium 0 what you need for, but it comes with a luggage of these extra ligand, DBA, triphenyl phosphine or so. These are not good ligand for your chemistry, so you don't want to get into there. Okay, now then the relatively next question immediately comes, how are you going to reduce palladium 2? What is the reagent that you use to reduce palladium 2? Yes, that's a great question. How do you reduce it? Usually the reagent that you use in the reaction mixture, like amine or phosphine, some part, because palladium is used really little tiny amount, and some part of the reagent that you are using, amine, these, or anything that you have in the reaction mixture, this is used as a reducing agent. Depending on the reaction condition, the reducing conditions or reducing agent will vary. Okay. So yeah, sometimes it's actually the phosphine which gets oxidized, the ligand phosphine that you are adding. Little tiny amount gets oxidized because tiny amount of palladium you are taking, phosphine oxides are formed, and or the amine can be also reducing the palladium 2 to palladium 0. Here is an mode by which this is the same ligand that you are trying to use. So this is your expensive ligand. With this expensive ligand, let's say very tiny amount of palladium, you have taken really palladium acetate. This eventually form phosphine oxide. Let's say 120 of these you started with, 5 or 10 of them form phosphine oxide, remaining 115 is for your main reactions, right? So there is nothing to really worry about. This goes on. This is the mechanism by which the phosphine oxide can be forming. Okay, so we'll stop here today up to here. If you have any questions, we can take it right now. Okay. Hi, Krishna.
Sir, how should I ask?
Okay.
I
Yeah.
understood
So
what you said.
yeah. Okay. So the last part was really practical part. That is what we were trying to discuss. That you start with cheap material like palladium 2 plus. You don't start with little bit expensive or sensitive material such as palladium 0. You use very cheap reagent and then you reduce it in the reaction condition or under the reaction condition. The reduction can be carried out by different mechanisms. Sometimes it is well understood, sometimes it is not. Usually the reagent that you are using during the reaction can be, one of those reagents can be the reducing source. Sometimes it is not well understood what is reducing palladium, because palladium is used really tiny amount there, like homeopathic amount in lot of cases, really tiny amount. Something usually amine or phosphine, because you have amine as a reagent because that is present in large quantity. Phosphine, again, you don't need a large quantity, small quantity, but part of that phosphine perhaps can be reducing your palladium too. And one of the way is over here, how phosphine is reducing palladium 2 plus. How it is happening? Okay, so you have started with palladium 2 acetate, you have phosphine ligand. It's a very expensive ligand for you. Okay, it's a very highly designed, just like what you have seen in the Grab's catalyst. The catalysts are really designed really beautifully. Similarly, this phosphine is not like triphenyl phosphine or tricyclohexyl phosphine. These are highly designed phosphine. It's going to be expensive phosphine. It's a bulky phosphine, big phosphine, right? Now these phosphine, first it forms a complex like this, palladium 2 acetate and 2 of the phosphine comes in, and then this sort of 8 complex palladium. This is the step which is a reversible step where palladium 2 is basically going to palladium 0. It's an 8 complex negatively charged species, and a positive ACOPR3 plus is getting generated, plus and minus gets neutralized, and subsequently this cationic species and this anionic species, water attacks. Water is tiny amount of water is in the reaction mixture. Water attacks on this phosphine to give you essentially phosphine oxide, and then you are ready to go with this ligand, the ligand palladium 0. So you in situ generate ligand palladium 0. We'll come back many other cases where you will see the amine is also reducing. There are different pathway by which amine is reducing. So this is always happening. Almost every reaction that you see, the high valent metal are used because they are cheap. They are readily available. You don't need any glove box or air sensitive condition. You can buy it from the market, but those are not the real catalyst. Real catalyst is something else that is getting generated inside the solution. Okay, you are not, the things that you are buying from market is the precursor, is the starting material to make the real catalyst. You make the real catalyst without sometime understanding what is going on. You do it, you put everything together in the reaction mixture, then you realize, aha, that's what is happening. Something else is really doing the chemistry, which is derived from those market available material. Okay, this is the pathway where you really generate, basically essentially this is you generate the real catalyst. This is the real catalyst. This you can say as a pre-catalyst before the catalyst is this step up to this step is happening. Okay. All right. Yeah, Krishna, if you have any question, we can try to answer here.
Sir, right now no question. I'll
Oh,
discuss after the class.
yeah. Okay. Yeah, after the class, we can always discuss as well. Thank you very much. I am now stopping it then. Okay. So see you soon.